Okay. So basically, my presentation is on modeling of quantum dynamics. So, what we usually show our initial conditions, which is different depending on the person, whatever you want to do. So, basically, we have a wave packet where this is the plane wave, and here is our Gaussian distribution. So basically, as I said, the P naught, as I said, the P naught is our initial momentum, and X naught is our initial position. Basically, here I plotted our real and imaginary part of the wave function just to show. And I'll focus more on talking about like the genetic methods on like plotting the genetic methods you can use to like find your wave function. So before I talk about all three methods, I would like to stress the importance that all three methods use the evolution operator to get the wave function. And in order for us, for the wave function to be used, we also need to use the Hamiltonian. And basically, method one use the momentum, the evolution operator in momentum space, whereas method 2 and 3 use it in coordinate space. So, as I said, method one basically use the momentum in momentum space and propagates it in momentum space, whereas in method 2, the momentum is used in coordinate space and then it's propagated in coordinate space. In method 3, the momentum is defined as the position space based on the derivative in finite differences and is propagated in coordinate space. So basically, here's method 1. So basically, in method 1, so the momentum before was defined in coordinate space. So basically, we're trying to transform it into a matrix because MATLAB works better with matrices. So in order to do that, we use a K space or K, basically, which K is the eigenvalue of the momentum, if I'm saying that correctly. So by using K, we basically convert our momentum operator into a matrix. And then after we have our Hamiltonian operator, which we know that is momentum squared over 2m. And yeah, basically after we type in the function, we get the method 1 basically. And then method 2 basically, as we use Fourier transform because we wanna convert our momentum back into coordinate space, and so we name it as px, and then after, which is also called as an alternative definition of momentum basically. So then after we have our Hamiltonian, which this time will be our the px squared divided by 2 plus our diagonal potential energy, and then after basically we also, using the Hamiltonian, will obtain a new evolution operator, and then after we plot our wave function. And then method 3 basically we use a Toeplitz matrix, which is basically a diagonal matrix in which all elements have the same values. So basically method 3 we convert it into a diagonal matrix, and then after we plot that, right? Yeah.
Okay, please join me in thanking Cybele. Are we relaxed enough to start asking questions?
Yes, I have one. Is there any reason to use method 1 and 2 over method 3?
Well, I'll say that the method depends on the research. So whichever method you find works along with whatever project you use, right? Okay. So whichever method works with the project, because I'm sure not all 3 methods will work with the project. So in my work, whichever one is easier and works better for your research project. Does that answer your question?
Yep.
Okay.
Excellent. So there are different definitions, and ideally they all should give the same
answer. Yeah.
But
and there may be more methods except from these three, but this is the three in the code. So I don't know if there's more, but they may be. So we may decide to.
So there's a challenge how to represent derivative in finite differences. Not and it's all dealing with this. More questions? So slide 7, please.
I don't know which one.
Yes, line 108. So it has symbol W twice.
Yes. So basically, we multiply our wave function times our momentum operator.
It's not wave function. Fourier transform.
Fourier transform by our momentum operator, and then by the conjugate of the Fourier transform.
So I'm very curious why. Just sure.
I said
if we follow Joshua and convert wave function from position to momentum, we apply Fourier transform once. And here you apply it twice. Why?
Because I'm trying to convert it back into position.
Because operator is a diagonal thing. Make sense? More or less. I have more questions, but we will fail in time. So excellent talk. Thanks, Cybele, once again.